Welcome, this is Dr. Plague. Now today I'm going to complete the design of the Plague Mark II homemade CPU. If you'll remember, in my last video we tested out the current design which supported 5 different CPU instructions. They were no op, add, out, jump if not carry, and halt. Now the out instruction was not quite complete yet, so I'll finish that up today and we'll add in 3 more instructions. And just an FYI, as I'm sure you already know, this completed design will not be very impressive and will present quite a few issues which prevent it from being considered a useful machine. It has quite a few shortcomings, such as we haven't organized the CPU very well. We haven't divided it up into neat little sections. For example, the arithmetic logic unit, the control unit, the register files, etc. And it's quite arduous to add new instructions to it. But it's just a start, and we'll address these shortcomings in the future when we design the Plague Mark III homemade CPU. So let's get started with the out instruction. The problem with the current execution of the out instruction is that we can't output different values. We can only output a single signal, which is a high on the out line, and it is low whenever the out instruction is not executed. Wouldn't it be nice to instead output different values? Let's say, maybe values from register A. Let's do that. What I'm going to do is to add in another register to hold the output value, and this will be the out register. And I'll connect the output from register A to its input. I'll just add in some LEDs to display the output value. I want to make sure the output value is cleared when the CPU first starts up or when it is reset. So I'll connect its clear input to the CPU's internal reset line. And instead of using the current out LED, I'll just connect that line to the clocking input of the out register. Now, whenever we execute the out instruction, we will simply copy the value from register A to the out register. The out register will always be active, and it will always output the last value that was copied into it. So, let's test this out. We know that register A starts out in the cleared state, so it doesn't really make sense to execute the out instruction before loading a value into register A. But let's test that out anyway. If we enter an out instruction, which is 20 in hexadecimal, followed by a halt, which is 80 in hex, and try running it, we get no output from the out register. So let's load register A with a value first. How about 5? To do this, we can simply add 5 to register A with 15 hex. Then we'll execute the out instruction, which is 20 hex, followed by halt, 80 hex. Let's run this. There, 5 showed up on the output, which is 0101 in binary. Perfect. Now let's output another value after 5. I want to output 9, so we'll add 4 to register A since 4 plus 5 is 9. Then we'll execute another out instruction, followed by a halt. Okay, let's run it. And beautiful, we get 9, which is 1001 in binary. Let's make this change on the breadboards. I'll add the out register 74273 IC right here. I'll connect power and ground, then add a bypass cap. We need to terminate the unused inputs on pins 13, 14, 17, and 18. I'll connect the outputs from register A to the inputs of the out register. Then we'll connect the reset line from register A to this out register. I'm going to disconnect the current out LED since we are now outputting a value. I'll connect output number 2 from the decoder to the clock input of the out register. And to output a value, I'll just add another LED bar graph up here. I'll give it an array of 470 ohm resistors to ground. Finally, we'll connect the outputs from the out register to the new LED strip. I'll skip adding more buffers to save space, since this is just a temporary build. Now, if we were using LS chips, then we would want to send it through a buffer first, but the HCT versions can usually supply enough current to drive the LEDs, so I'll just connect the outputs directly to the LEDs. Okay, let's get this flash chip out so we can reprogram it. I'll program in the code we left off with in the last simulation. Yeah, that looks good. Let's put it back on the breadboard. Okay, let's give it the test. We get 5, followed by 9. Perfect. Now, notice in the last example we had to load a value into register A by executing an add instruction. Wouldn't it be nice to have an actual load instruction? Actually, I'm going to call it copy, because that's exactly what it does. It'll copy a value from a memory location into register A. And I'll use 5 for its opcode. It'll take an immediate value, I, and copy that into register A. To accomplish this, we need to somehow connect the immediate operand value to register A. And there are several ways we could do this, but I'll just show one method. We already have the operand connected to register A through this here adder. So we could put a mux on the adder's output, which would let us select whether to send the adder output to register A or send the operand directly to register A. But instead, I'll put the mux between the output of register A and the input of the adder, like this. And if we go inside of the mux, we can see that I'm using a 74 series 157 quad 2-input multiplexer, and pins 2, 5, 11, and 14 will be used for input 0, while pins 3, 6, 10, and 13 will be used for input 1. The output of the mux will come from pins 4, 7, 9, and 12. There's an enable on pin 15 and a select input on pin 1. This selects which of the two inputs gets sent to the output. A low on the select input will send input 0 to the output, while a high will send input 1 to the output. Now, when we want to copy a value to register A, we don't want to add anything to the operand, so I'll just connect all the inputs of input 1 to ground. I'll keep this mux enabled at all times, so I'll just ground the enable pin. Alternatively, we could use the enable pin to send a 0 to the output, but I'll just keep it this way since we need to terminate all inputs anyway. Now, I want to clock in a value to register A whenever we execute this copy instruction, but we already clock register A during an add instruction. So, I'll just use an OR gate to send both the add and copy opcodes to the clocking pin of register A, that is, opcodes 1 and 5. And I'll be using a 74 series 32 IC for the OR gate, which contains 4 OR gates. So I'll just place the unused OR gates over here. Now, here comes the interesting part. We need to set up input A of the adder to the current selection from the mux, but we need to do so before we clock in the value to register A. If we try to simultaneously select the mux value while clocking the input to register A, then we'll miss the correct value due to a propagation delay from the mux input and through the adder. We need to select the mux value before we clock register A. How can we do this? Well, each instruction uses two levels of the main clock, a high and a low. The value from the adder gets clocked into register A during the middle of the instruction, when the main clock transitions from high to low. So, we need to select the mux input while the main clock is high. There are some various ways we could go about doing this. What we could do is add in a second 3 to 8 line decoder right here. We'll call the first one the instruction execute decoder, and the second one the instruction setup decoder, since it will be used to set up the instruction before executing it. I'll take all the address inputs from the first decoder and send them to the second decoder. Then I'll send the enable lines from the first decoder to the second decoder. That is, all, but not the one coming from the clock. Instead, I'll just ground that input to the second decoder. Can you see what that does? The second decoder will not be dependent on the level of the clock. Therefore, it will fire throughout the entire instruction cycle. Beautiful! I'll just send output number 5 of the setup decoder to the select input of the mux. The second decoder will now select the correct mux input before the first decoder clocks the value into register A. Perfect. Let's test this out. I'll use the same code as before, but this time change the adds to copies. And I'll copy 5 followed by 9. That'll be 55 and 59 in hex. Now we should get the same result as before. Let's run it. Works fine. But you know what? I don't really want to add in another decoder just for one instruction, so let's take that out. Instead, I know that both instructions that need to set up the mux, which are add and copy, have opposite values on the third bit of their opcodes. Add has an opcode of 1, so its third bit is a 0, while copy has an opcode of 5, making its third bit a 1. We can take advantage of this by just sending the third bit of the opcode directly to the select input of the mux. Now, I'm not saying that this is a good way of doing this. I'm only doing it to save an IC. So, let's test this out to make sure it still works. And I'll just add in an add instruction at the end to test that out. I'll add 2, which is 1, 2 in hex, then the halt. Now, the out register should end with 9, and register A should end with 11, which is 1011 in binary. Let's run it. And of course, it does work. So now, let's update the breadboards. I'll add the 74157 mux right here, and give it power, ground, and its bypass cap. I'll ground the second input nibble of the mux, pins 3, 6, 10, and 13. Then I'll ground the enable pin, which is pin 15. I'll disconnect the output of register A from input A of the adder. Then connect the output from register A to input 0 of the mux. It's getting a little tight, but we'll get it connected. Now, I'm going to connect the output of the mux to input A of the adder. I'll connect the third bit of the opcode from the 238 chip to the select input of the MUX. Let's add the quad OR gates, the 7432, down here. Then that'll get power, ground, and a bypass cap. I'll just terminate the unused inputs. Then I'll send output numbers 5 and 1 from the decoder to the inputs of the OR gate. I'll need to disconnect output number 1 first, which was going to the clock input of register A. And finally, I'll connect that clock input from register A to the output of the OR gate. Let's take out the flash chip again to add in the new code, and I'll reprogram it before adding it back to the breadboard. Here it goes. We should get a 5, then a 9 on the output, and end up with 11 in register A. Beautiful! That's exactly what we got. Let's continue. We have an out instruction, so wouldn't it behoove us to create an in instruction? Let's do that next. I'll select 3 for its opcode. And there is no operand, so I'll just X that out. So I'll just add in another register right here for the input to come into. And we'll just add in some LEDs for now and call this register B. So now we have 4 registers basically. The instruction pointer, which is contained in this counter up here, the out register, register A, and now register B. I'll add in some switches to act as the input. Then I'll send output 3 from the decoder to clock the input into register B. Finally, I'll connect the internal reset line to the clear input of register B, so we start out with a value of 0. And that's it. We can now take input, but there's not much we can do with it yet. We'll get to that shortly, but for now, let's test this out. I'll just add on to our program and grab the input before the halt. 30 hex. Let's run this. I'll set the switches to 6. And it gets clocked in just fine. We have 9 in the out register, 11 in register A, and 6 in register B. Time to update the breadboards. Let's put register B, the 74273, right here next to the out register. And of course, I'll give it power, ground, and a bypass cap. We need to terminate the unused inputs on pins 13, 14, 17, and 18. And I'll send output 3 of the decoder to the clock input of this register. I'll just connect the resets of these 2 chips together. We need to get the outputs of this register up to the LEDs. And this is kind of like performing a little bit of surgery. Who says that electrical engineers aren't surgeons? Now, admittedly, this is getting to be quite a messy build. I wouldn't suggest that you build your projects like this, but since this is just a temporary build, I'm just going to go with it. This mess of a build would not be suitable for high-speed operations, but should work fine for my demonstrations. I'll add in the switches that we built in a previous video. Then connect them up to the inputs of register B. Again, we need to take out the flash chip to reprogram it with the latest code. Okay, that should do it. Let's test this out. We should end up with 9 in the out register, 11 in register A, and whatever we press on the switches in register B. I'm pressing 6 first, and we do get 6 in register B. Let's try 9. And register B clocks in 9. How about 5? Yep, that works too. Fantastic! Okay, I'm going to add one more instruction and then call it quits for this CPU. You can, however, still expand upon it and have whatever fun you want with it. But I want to move on to the Plague Mark III sometime soon. Now, I want an instruction that is going to make use of the input value. So, why not another conditional jump? I'll make a jump if equal instruction, JE, and I'll choose 6 for my opcode. And of course, it'll have an address for an operand. Now, what this instruction is going to do is jump to the address in the operand if the contents of register A are equal to register B. This will allow the CPU to make decisions based on the input value. I'm going to add a comparator down here. And if we go inside of it, we can see that I'm using a 74 series 688 logic 8-bit magnitude comparator IC. We can see that there are 2 8-bit inputs going to one output, with an enable input. I'll only be using 4 bits from each input and just ground the other inputs. This IC will output a low only when it is enabled and input A is equal to input B. So let's connect the output from register A to one of its inputs, and the output from register B to its other input. And I'll just keep it enabled by grounding its enable pin. Now we have 2 instructions, jump if not carry and jump if equal, that both need to connect to the load pin of the instruction counter. And since we now have unused OR gates, I'm going to replace this AND gate with one. Then I can swap the inverter to the other input and get rid of the inverter on the output. It should still work the same. As you can see here, with the different combinations of inputs, we get the same outputs. Now, I can send the output of the OR gate to the input of an AND gate and pull the other input of the AND gate to VCC. This will still work the same, but now we can use the other input of the AND gate for the other conditional jump instruction. So, I'll use output 6 from the decoder and the output from the comparator to connect to the other input of the AND gate, like this. Now both conditional jump instructions can load the instruction pointer with an address value when needed. Now, I probably could have done something more fancy, such as to send output 6 from the decoder through an inverter to the enable of the comparator. Then the comparator output could bypass the bottom OR gate before the AND gate to save an OR gate. But I like it the way it is. And this just shows you that there are many ways to do the same thing. Let's give it a test. Let's write some code that will check if our input is equal to 7. And if so, output a 1, else output a 0. First, we'll copy the value of 7 into register A, 57 hex. Then we'll get input from the switches, 30 hex. I'll jump if equal to address 4, 64 hex. If we get to address 3, then the input was not equal to 7. So I'll just halt, since the output will already be 0. So 80 hex. Now if the jump if equal instruction jumped to address 4, then I'll copy the value of 1 into register A, 51 hex. Then I'll just send that to the out register, 20 hex, before a halt, 80 hex. Okay, let's give this a shot. I'll leave the input switches as is. This will be a 0. And if we run it, we can see that we get to the halt at address 3 with an output of 0. Let's reset it to try it again and input a 6. And we still get a 0 on the output. Now let's set the switches to 7 and give it a reset. And yes, we get a 1 on the output. Stupendous! Let's make this final change to the breadboards. I'll just place the 74688 8-bit logic comparator in this last spot right here. Give it power, ground, and the bypass cap. I'm going to send all the unused inputs to ground. I'll ground the enable pin. Then connect the output from register A to input B of the comparator. And I'll connect the output from register B to input A of the comparator. I'll unterminate 2 of the OR gates. Then I'll rearrange the inverters, OR, and AND gates to match the circuit in the simulation. And finally, I'll connect the output from the 8-bit comparator to the OR gate. Let's remove the flash chip one last time to put the latest code into it. Now remember, with this code, we'll get an output of 1 in the out register if and only if we input a 7 on the switches. Any other input on the switches will result in an output of 0 in the out register. Okay, let's run it. With an input of 0, we get an output of 0. Now, I'll press 4. And that gets captured into register B, and the out register is still 0. Okay, 7. We should get a 1. And we do. Let's do something a little different this time. I'm going to crank up the clock frequency to its max to see if this CPU still works at higher speeds. We should get to a little north of 10 kilohertz. And if we take a quick measurement, yeah, we're at about 10.13 kilohertz. Now, at this speed, the output should be pretty much instantaneous. And if I reset it with a 0 on the input, we get an output of 0. Next, I'll try inputting a 5. Register B captured 5, and the out register is 0. Now 8. Still outputs 0. Let's try 10. And we still get an output of 0. Now 7 should give us a 1, and it does. And it is repeatable. Now back to 0. Perfect! Now in the beginning I mentioned that the final Plague Mark II CPU design would use around 12 logic ICs. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Perfect! I was spot on. How many other CPUs made out of discrete logic ICs do you know of that can execute 8 instructions with only 12 logic ICs? I'm sure there are others out there, but are there any as bizarre as this one? Well, that's going to wrap it up for this video. In the next video, I plan on updating the assembler that we created, and I'll perform one final test of this Plague Mark II CPU. Kind of like what I did in the last video, something a little more practical. Then, that'll be it for the Plague Mark II before moving on to bigger and better things. After we finish up with the Plague Mark II, I plan on looking at some composite video circuits so we can have a better way to display output from the next homemade CPU, the Plague Mark III. Well, I hope you've enjoyed this video, and I'll see you next time, right here on Dr. Plague.